Everyone. So in today's lecture we will study linear combination and span. So in the last lecture I have already introduced you with the vector addition, scalar multiplication and basis vector. So today we will start our lecture with our first topic, which is linear combination. Linear combination of vectors. All right. So if you remember, last time I have given you an example where I have given one vector, one 2D vector 1 comma 0 and another 2D vector 0 1. This is I hat and j hat, and I combine these two vectors to get 2 comma 2, right? So what I said is 2 comma 2 can be is nothing but a combination of these two vector 1 comma 0, and it is nothing but 2 times the vector 1 comma 0 plus 2 times the vector 0 comma 1. So this thing is nothing but linear combination. So if I give you a general representation of it, so a vector c can be written as a, which is a scalar, times the vector v, plus b, which is another scalar, times the vector w. So now what is a, b, w, v, w? So let us suppose we have this 2D plane. All right, we have this 2D plane, and let us suppose this is vector a, this is vector vector v. Let us suppose this is vector v. All right, and let us suppose we have another vector, this is vector w. Okay, so as I already told you that multiplying a scalar with any vector is nothing but stretching or squishing that vector by some amount. So if a is greater than 0, then basically it means that we are stretching if a is greater than equal to 1, if a is greater than 1, then that means we are stretching the vector. If a is less than 1 and greater than 0, then that means we are squishing the vector, and if a is less than 0, that means we are inverting the vector. And there are a special case where a equal to 1, which basically means we are doing nothing, right? So when I am doing this a times vector v, this is nothing but scalar multiplication. I am stretching or squishing the vector v, and same with the vector w. And then this vector addition is giving me a combination of these two vectors, right? So the vector c is nothing but a combination of two vectors v and w. And what type of combination it is? It is linear combination. It is linear combination, right? Because we have simply scaled the vectors and added them, so it's a linear combination. So if you see, let us suppose if we take these two vectors, let us suppose this is vector v, and let us suppose this is vector w, right? So these two vectors, any linear combination of these two vectors will fill the xy plane, right? What I mean by filling the xy plane? By filling the xy plane, I mean to say any vector c which belongs to space R2 is nothing but a linear combination of these two vectors v and w, and this is true for any vector. All right, and the same terminology goes for three-dimensional vector as well. So in 3D we have, let us suppose we have a 3D vector d. So it is nothing but a linear combination of three-dimensional vector a, v, w, b, and let us suppose this is gamma, c times gamma, right? And if these three vectors are not linearly dependent, I will explain what is linearly dependent or independent. Then any vector d belonging to R cube is nothing but a linear combination of these three vectors. But there is a condition, like this will be true only if these three vectors are linearly independent, and I will explain what is linearly dependent and linearly independent in a couple of moments. So when I say this filling the xy plane, when I am saying this filling of xy plane, so first of all, the basic definition of LC, which is linear combination, is linear combination of any two vectors v and w is nothing but a v plus b w, and here a and b are scalars. All right. Now there is an extension of this this filling the plane and all those things, which we called as a span. Okay, so span is nothing but it's a span of any two vectors, span of any two vector v and w is the set of all linear combinations of v and w, all linear combinations av plus bw, and here a and b belongs to R. So a and b can be any real value. So you see that when I say I have two vectors v and w, let us suppose this is v and this is w. So the span of v and w is any combination of these two vectors, any linear combination, by the way, this is very important, any linear combination of these two vectors. So in this scenario, because see these two vectors are independent, I mean they are not coinciding. So if you take all the linear combination, because it is the set of all the span is the set of all the linear combination. So if you take all the linear combination, then you will get the entire xy plane, right? You will get the entire xy plane. So span of any two vector is nothing but set of all linear combinations of those two vectors. Okay, now there is an interesting understanding behind this span and all. So for example, let us suppose we have this xy plane, right? We have this xy plane and we have one vector here, this is v. All right. Let us suppose this vector v is nothing but 1 comma 1, let us suppose, and let us suppose we have another vector here which is w, and let us suppose this is 1 minus 1. Okay, now we will first see what AV means graphically. A into V, here A is a scalar and A belongs to R. A could be any real value. So if you see, this is the vector A. So if you multiply this 1 with let us suppose 2, you will get another vector 2 which is somewhere here. If you multiply with it let us suppose minus 1, then you will get minus 1, right, which is somewhere here, right? So if you see this AV, this AV where A belongs to R, this AV where A belongs to R is nothing but this entire line, right? This entire line is AV, right? So this entire actually it's not line, it's set of vectors. The entire set of vectors lying on this line is AV, right? Now if you see the span of vector V is nothing but a line, right? It's just a line, because what is a span of V? Span of V is all linear combination of V, right, such that AV where A belongs to real number. So the span of any vector is nothing in 2D. If you take any vector in 2 dimension, then the span of the vector itself is a line, right? except the special vector with the zero vector, because the span of zero vector is just zero vector, so it's not a line. But apart from the zero vector, any vector on the 2D plane, the span of the vector itself is a line, right? So the span of the vector v is nothing but a line, right? Now the same is true for w. The same is true for w. If I take the span of w, which is bw, where b belongs to all r, then this is also set of all vectors lying on line bw, which is this one, right? Now this interesting thing. Now you see that AV is nothing but forming a line, BW is also forming a line. Basically AV is set of all vectors lying on a line, BW is set of all vectors lying on a line, and these two lines are not coinciding. You see these two lines are not coinciding because the vector V and W are not coinciding, which basically means they are linearly independent. So the combination, which is the addition of these two vectors, will give you a plane, XY plane. And that's why the span of V and W is entire XY plane. All right. So I think you get the intuition what is a span and how the span of these two vectors is giving the entire XY plane. So always the main thing you need to remember here is any 2D vector in XY plane except the zero vector, which is an exception case, except the zero vector, any 2D vector in XY plane has span as a line passing through that vector, right? Or you can also say that span of any 2D vector in XY plane is the line passing through that vector. All right. And when we take such two spans, the two one-dimensional spans which are not coinciding, which are independent, then the combination of those two spans, those two 1D spans become a 2D span. All right. So that's why this terminology come that these two vectors V and W, which are linearly independent, fills the entire XY plane. By filling, I means that you can get any vector using these two vectors, right? So if you remember in the last lecture, in the basis vector thing, I introduced that I hat and j hat fills the XY plane, right? Why that is the case? Because I hat and j hat are not coinciding each other, they are linearly independent. So the span of I hat is nothing but the sorry, I hat is here and j hat is here, right? So sorry, I will redraw the diagram. So I hat is here and j hat is here. So what is the span of I hat? Span of I hat is nothing but x-axis, right? And what is the span of j hat? Span of j hat is nothing but the y-axis. And span of LC of I hat and j hat, LC is linear combination, is xy plane. So this is very important. If you get this, how the span of I hat is x-axis, then this is simple, because the same analogy goes for span of j hat, and the span, these two spans, these two 1D spans which are independent of each other will give you, the linear combination of them will give you the xy plane, right? And the same analogy goes for 3 dimension, where we have I hat, j hat and k hat. All right. So I think this span is clear to us that what is a span. It's very basic thing, right? Now I will just mention few important points related to span to make the things even more clear. So the span of okay, I will first introduce you with the topic linearly dependent and independent. Just give me a minute. All right. So what is linearly dependent or independent? All right. So if you remember, when I was saying this, the span of V and W fills the entire plane, right? Same goes for that I hat and j hat. The span of I hat and j hat is nothing but the entire xy axis. Here see, this V hat and W hat, it is giving me the entire xy plane, right? So is it true for all set of vectors, all 2D set of vectors? So my question is the span of any 2D, any two 2D vectors is always xy plane? This is my question. So you may pause the video and think about it. So before that, let us suppose let's just check this thing. Okay, so we have already checked this scenario where the two vectors are not coinciding with each other, V and W. So in this case, the span okay, by the way guys, this is the notation how we write span of V comma W is R2. So this R2 basically means xy plane. So span of V comma W is R2. So this we already have seen, this is true, right? Now let us suppose I have another scenario. All right, let us suppose I have one vector V here, and let us suppose there is another vector which is in the same on the same line but opposite to it, W. Now what is the span of V and W? Is it R2? This is the question. Is what? So see, what is the span? The definition of span, basically it is nothing but the linear combination of these two vectors, right? So span of V and W is nothing but linear combination AV and BW. And when I am saying linear combination, you have the visual idea interpretation of it. Okay, this is notation wise notational maths, but you should have the visual interpretation, which I have already explained to you here. What is a span? What is the span of V? What is the span of W? And what is the span of linear combination of V and W, right? So here span of V is what? It is nothing but the set of all vectors passing through this line. I mean set of all vectors which are lying on this line. All right. And what is the span of W? Set of all vectors which are lying on this line on which W is lying. And what is the span of linear combination of the V and W? Is nothing but the span of linear combination of these two set of vectors, which is nothing but xy plane. Okay, so what is this? What is this? This is set of all vectors passing through A. So set of all set of all vectors passing through V, right? So this is set of all vectors passing, or we can also say parallel, maybe passing is the right notation, passing through V, right? So this is nothing but this entire line, right? So this is A times V, right? And what is this? This is also set of all vectors passing through W, right? And see, W is also already passing through this A comma B. So this is nothing but this is also BW. So if you see the span of V and span of W is lying on the same line. The span of V and span of W is lying on the same line, and we already know that span of any 2D vector except V is R, right? So that is true for W also. This is R. This is true for any vector, any 2D vector except the origin, right? Now because the span, these two set of vectors are lying on the same line, so we cannot have any linear combination which will give us a vector outside this span, outside this line, right? If you take any two vectors in this linear combination, I mean any two value for A and B, any two value of A and B, any two values of A and B cannot give a vector outside the span of V or span of W. Okay, you take any combination, you always remain in this line. So it is like this is kind of a jail for you now. These two vectors are stuck in this 1D world. So if you see this entire xy plane is a 2D world, but these two vectors are now stuck in this 1D world because they already kind of lies on the same line, and any linear combination of the both of these vectors will give you a vector on the same line. So you will always remain in this R. So span of V and W is nothing but just R. Okay. So why this is the case? Because V and W are linearly independent. This is the case. Span of V comma W is R. This is because V and W are linearly dependent. What I mean by linearly dependent? It is very simple that V is nothing but some alpha times W, some linear combination of some scaled value of W, and that makes sense, right? You may be saying that okay, V is pointing in this direction, W is pointing in this direction, then how is it possible? That's very simple. Then in this case alpha is nothing but a negative value, right? So let us suppose maybe V is 2 comma 2, example, for example, V is 2 comma 2, W is, let us suppose, -1 comma -1, then alpha is nothing but -2, right? So if alpha into W is nothing but 2 comma 2, which is V, and same for W also. W is nothing, some beta times V, and here beta is also negative, right? So here in this case, in particular case, beta will be -1/2, right? So you see that because V can be written in terms of W, so the vector V can be written in terms of W, and same for W. So V and W are linearly dependent. So this particular any two vectors are linearly dependent if one vector V can be written in terms of another vector W. This is the simplest definition of linearly dependent vector. And V and W can be of any dimension. V, W can belong to Rn. It could be R, R square, R cube, anything, right? So the original question, is the span of any 2D vector is always xy plane? The answer is a big no, right? The answer is no. Why so? Because what if I take these two vectors? Let us suppose I take this vector 1 comma 0 and 2 comma 0. So this is 1 comma 0 and this is 2 comma 0, right? So the linear combination or the span of these two vectors 1 0 and 2 0 is nothing but x-axis. Span of 1 0 2 0 is nothing but just x-axis, which is r. So the span of any 2D vector won't give the xy plane. So the xy plane, what is the condition to get an xy plane? That both the vectors should be linearly independent. So here we get that any two linearly independent 2D vectors span the entire R2. Any two linearly, and this is important, that any two, right? Any it's not necessary it should be I hat or j hat, right? Any two, all right, but it should be linearly independent. It should be linearly independent. That is the only condition. All right. Now I will be just mentioning few important just to make sure that span is clear. So at after every statement, just pause and think about it, like if I am making sense or not. So span of two linearly independent 2D vector is r square. This is basically xy plane, right? Make sense? Second thing, span of two linearly dependent, not independent 2D vector is what? Is just r, which is line in xy plane. It's a line in xy plane and it's the entire xy plane, right? Now let's move to 3 dimensions. We have span of two linearly independent, all right, this is independent 3D vectors. Now we are moving in this 3D space. So we have the 3D space, we have 3D vectors, but we have just two of them. So what is this? Is it going to be the entire xyz space r cube? No, it is just going to be r square. Is an xy plane in 3D space. That is, it is r square in r cube, right? So r cube is the entire 3D space, and this span of two linearly independent vectors is r square. So see, first of all, why it is r square? Because see, we have 3D space, but we have given only two vectors. So to span the entire space, we need entire 3D space, we need at least 3 vectors, right? And we are given only 2 vectors. But because these are linearly independent, so it's just in r square. But let us suppose the same thing. If span of two linearly dependent 3D vectors in xy plane is in xyz plane is r. All right, you got my point. So span of two linearly dependent 3D vector is just r in r cube, right? So because you have just given two vectors and that also linearly dependent, so it will form a line only, right? So similarly you can do all this combination, but I think you got the idea what is linearly dependent and linearly independent. So just to give an visual interpretation in 3D space, all right. So let us suppose in 3D space we have this plane. In 3D space we have this 2D plane. This is z-axis, all right, and this is, let us put this y-axis, and this is the x-axis, and this is the origin, all right, 0 vector, and let us suppose we have these two vectors w and v. All right, so here we can clearly say that v, the vector, the 3D vectors v and w are linearly independent. It's pretty evident from the diagram itself because they are not coinciding. Linearly independent 3D vectors, and their span, what is a span? Set of all vectors, set of all linear combination of v and w is a xy plane passing through origin. All right, and guys, one more thing, that this is a subspace. This is a subspace also. I will, like, subspace is, will have a different video, but just giving you that this is a subspace also. All right, okay, so okay, just one more thing. Now let us suppose here we have two vectors v and w, right? And we know that z, let us suppose z is another vector which is nothing but linear combination of w. So the span of v comma w is same as the span of v comma w comma z, which is r square. And this is an important thing. Why? Because see, the maximum number of vectors, linearly independent vectors we need to cover this entire xy plane is just 2, right? Because once you get 2 linearly independent vector, no matter how many additional vector you keep on adding, let us suppose after z you add vector y, vector alpha, vector beta, and keep on adding, it won't add anything to the span, because all these vectors z, y, alpha, beta, gamma, and so on are nothing but a linear combination of these two vectors v and w, right? So this v and w, this linear combination may be this, let us suppose a and b is 1, then this vector is nothing but sorry, not this one, but yeah, here somewhere here you will get the vector z, right? You will just this is vector z. Okay, so this is an important thing, that no matter how many vectors you keep on adding to this particular set, the span is always be r2, which is the span of v and w. All right, but let us suppose in this scenario, in this above scenario, all right, we have v and w. Let us suppose in this case, because v and w are 3D, right? Here I will add another vector z, and this z is not a linear combination of v and w. What does that mean? That this z lies outside the plane. The z lies outside the plane, or you can also say subspace containing v and w, right? Because if it lies in the same plane as v and w, then it must be a linear combination of v and w. That is by definition. That is by definition. If you combine these two vectors, then the third, if you take a linear combination of these two vectors, then the third vector will always lie in this plane. That is by definition of linear combination. But if I am saying that if z is not lying in this plane, then it must be a vector, some vector outside this plane. This maybe, let's draw, it is perpendicular to this plane. It's not necessary to be perpendicular, but just let us suppose outside this plane. Now the span of v, w, and z. Now the span of v, w, and z is r cube, whereas the span, just the span of v and w is r square, right? So we can tell how this thing became, like, we already know that span of v comma w is nothing but r square, right? And I also already explained that span of just z is r, right? And because z is not a linear combination, it's not a linear combination of v and w. Therefore these two spans are not a linear combination of each other. I mean these two spans are lying I mean this span of z is not lying in the span of v and w. So then if you combine these two spans, that r and r square, so if you see this span of r, this is this line which is going outside this plane, then the combination of these two spans, this plane and this line, will give you, from here you will get span of v w z is r cube, right? We did this the same exact thing here, right? Same thing we did here. See, I mentioned that the span of v is r, the span of w is r, and then the span of v and w is r square, right? Here the span of I hat is x axis, the span of j hat is y axis, and the span of linear combination of I hat and j hat is xy plane. All right. So similarly this thing, because the vector z is lying outside the plane containing v and w, so that means it's not a linear combination of v and w. So the span of this plane and this line is the entire 3D space. And you can also think like, for example, this is the plane, right? This is this, I have drawn this, but planes are infinite, there is no such boundary as such, so planes are infinite. So you can think that this using this line, if this line is not there, if the z vector is not there, then this plane is stuck in this particular 2D space. But with the help of this line, this plane is kind of sweeping the entire 3D space, kind of sweeping the entire 3D space. You have this plane, you take this vector, you get a plane here. You have this plane, you take another maybe this vector, you get a plane here. So similarly all the combination will give you the entire 3D space. All right. So I think it is very clear to you what is linearly independent and linearly dependent vectors. All right. So the very basic definition is this: if vector v, it can be written as some scaled value of vector w, then v and w are linearly dependent vectors. All right. Okay. So we can say that any two linearly independent 2D vectors span xy plane. All right. Any two linearly independent 2D vectors span xy plane. All right. Now at the end I will just mention the basis vector concept as well, from the point of spans. Last time I already introduced it. Basis vectors. All right. So now we will get to the definition of basis vectors in terms of span. So the basis vector, the basis of a vector space, basis of a vector space is a set of linearly independent vectors that span the full space, right? So in the last lecture I already told you that for 2D space the standard basis for r square, standard basis for r square is nothing but I hat and j hat, right? But this is the standard basis, but we can take any 2D vector as a basis vector for our r square, but it should be linearly independent. So I can take these two vectors also. I can take one vector this and another vector this, v and w. So v and w are also basis vectors for r square. Similarly these two vectors, this one this vector, or maybe another this vector, these two vectors are also basis for R square, but these two vectors W and this V, this V and this W cannot be the basis for R square. Why? Because these are not linearly independent, these are linearly dependent, and if they are linearly dependent, then they won't span the entire xy plane, they won't span the entire R square, right? So I think you get get the idea that what is basis. So basis is originated from the word base, right? So when I say that I hat and j hat are basis for R square, I mean they are the base for R square, they are the base for xy plane. What I mean base, that any vector in R2 R square is nothing but a linear combination of I hat and j hat, and same thing is true for any other vector v and w, given that they should not be linearly dependent, they should be linearly independent, because if they are linearly independent, then only I can get any other vector using the linear combination of these two vectors, right? Because using the linear combination of this v and this w, I cannot get this vector, right? Because this lies outside the span of these two v and w, the bottom one, right? So I think you got the idea what is the basis for a vector space. Basis for a vector space is nothing but a set of vectors, set of linearly independent vectors that span the entire full space. Now there is an interesting question. Okay, I say that okay, I hat and j hat are linearly independent, but is I hat j hat basis for R cube? Because see, I hat and j hat are still linearly independent, so they should also be the basis, but no. Why? Because apart from linearly independence, you should also satisfy this thing, it should span the full space. So I hat and j hat in R cube, so if I take R cube, this is R cube, alright, and let us suppose this is x axis, this is y axis, and this is z axis. So I hat and j hat is this plane, is just this plane, it will just span this plane, and we are missing the vectors which are perpendicular to this xy plane. So I hat and j hat is not a basis for R cube. So to make the basis set for R cube, we need to add, apart from I hat j hat, we need to add another vector v. It could be any vector, given that this vector v should not be a linear combination of I hat and j hat. And in visual terms, in terms of figures, I mean to say that v should not lie in this xy plane. It should be any vector outside the xy plane. It should be any vector outside the xy plane. So it could be this vector which is outside the xy plane, it could be this vector, it could be this vector, this vector, this vector, any vector, but it should be outside the xy plane, right? And we know that the standard one is I hat, j hat, and k hat. This is the standard. K hat nothing but the unit vector in this direction, right? So basis for a vector space should satisfy two conditions. First of all, linearly independent, and second is span the full space. And to be very frank, linearly independence doesn't always imply spanning the full space, right? Because if you are in R cube and I give you only two vectors which are linearly independent, then it is not spanning the full space. But vice versa is true. If I am saying that I have given a set of vectors which span the entire R cube, then that means if I have given you three vectors, not a set of vectors, if I have given you three vectors and I am saying that they are spanning the entire 3D space R cube, then for sure they are linearly independent. But if I have given you any set, let us suppose I have given you three vectors, v1, v2, and v3, right? And I am saying that let us suppose this is a set S1, all right, and I am saying that span of S1 is R cube. Let us suppose I am saying this one. What does this imply? This implies that v1, v2, v3 are linearly independent, all right, are linearly independent. But let us suppose I have given you another set S2. in this set I have given you more than 3 vectors v1, v2, v3, and let us suppose I have given you one more vector v4, and I have I told you again that span of S2 is also R cube, but this does not implies that v1, v2, v3 and v4 are linearly independent. Why? Because I have already told that to span the R cube all you need is just 3 linearly independent vector, and you have given me 4. So that means that one of the vector, any one of the vector, is nothing but the linear combination of the remaining 3. So this entire set is not linearly independent. Alright. So yeah, so that's it for today's lecture. I think covered a lot of important things. So just revisit this video again and again if something is not clear to you. This is very important topic, by the way, linear combination of vectors in span, because the upcoming topics, the linear transformation, is highly dependent on how you like interpret this linear combination and spans. Okay guys, then if you found these videos, these lectures very helpful, then hit the subscribe button, like my videos, share my videos with your friends, with your colleagues, with any GATE aspirant or any ML engineer. Alright, so thank you, see you next time.